linear differential equations of order n with constant coefficients. Now we have already seen linear differential equations in their simplest form. And what was that? Comprising of x, y and dy by dx. Then we saw linear differential equation with x, y and higher powers of dy by dx, that is dy by dx square, dy by dx cube and so on. And if you remember, we said since repetitively we might have to write dy by dx, so we said let p is equal to dy by dx. Okay, so now let's look at linear differential equations with constant coefficients of order n. So the general form would look like this: a naught d nth derivative of y with respect to x plus a1 d n minus 1th derivative of x with respect to y with respect to x plus a2 d n minus 2th derivative of y with respect to x and so on till we reach a n and we end up with y, and this whole thing is equal to f of x. So here, just for general this one, remember there are two ways of looking at it. A way of writing a function in terms of constant coefficients and successive derivatives, right? Another way is to look at it is writing a series comprising of constant coefficients and successive derivatives as a function. Okay, now again, if you noticed here, it is going to become tedious to write the nth derivative in this form. So let's come out with a separate notation. Let's say d is equal to d by dx. That means we can write d square is equal to the second derivative of with respect to x. Similarly, d cube we can use instead of the third derivative. Yes, so instead of writing dy by dx, we can say dy. Instead of writing d square y by dx square, we can write d square y. Similarly, d cube y by dx cube, we can write it as d cube y. Basically to simplify the writing. So using this notation, our general form, this one, will look like this: a naught dny, nth derivative, plus a1 dn minus 1y plus a2 dn minus 2 the derivative, and so on till we reach a n y is equal to f of x. Now we can write this as a naught dn plus a1 dn minus 1 plus a2 dn minus 2 and so on up to a n times y is equal to f of x. And now we can take this y to the other side, so that f of x by y is equal to a naught dn plus a1 dn minus 1 plus a2 dn minus 2 and so on up to an. Now this we can write it as if it is a function of d. So which means this becomes f of x by y is equal to capital F of d. Or we can say f of x is equal to capital F of d times y. D is treated as an operator and it satisfies the following laws similar to algebra, fundamental laws of algebra. This operator would follow. So what are they? D u plus v is equal to du plus dv. This is nothing but distributive law. Second one is dm dmu dnu is equal to dm plus n. Now here remember m and n belong to positive integers. Okay, the third law is dcu is equal to cdu. That means here c is a constant. Okay, fourth one dm dnu is equal to dn dmu. Again here m and n belong to positive, very importantly not commutative. That is dmu times dnv is not equal to dmv times dnu. And index laws don't apply to negative powers, because if we have negative powers, it's treated as a fraction. Okay, so which means we can manipulate f of d using above laws. Okay, now there are certain results which can be very useful in solving these differential equations. One of them is f of d times e to the power of ax is equal to e to the power of ax times f of a. Okay, let's see how we can prove this. F of d eax can be written as, remember f of d, a naught d3. Let us say we are talking of n equal to 3. By just putting different values of n and expanding it accordingly, we can prove for any n. So here we are taking it as 3 plus a1 d square plus a2 d1 plus a3 times e to the power of ax. Okay, now here, okay, this is equal to, let's distribute eax. So a naught d3 e to the power of ax plus a1 d2 eax plus a2 deax plus a3 eax. Okay, now let's take one by one. Now if we look at d square eax, what is this? This is derivative, second derivative, right? So second derivative, so this can be written as d square eax by dx. This can be written as d by dx of, let's differentiate it. So this would be what? EAX, and then the derivative of the exponent, that is A. Similarly, again we differentiate. So we get AEAX and another A. So which we can remove and says A square. So this becomes d square EAX. Now EAX gets cancelled and we are left with d square is equal to A square. Similarly, for the third derivative or the first derivative, whatever, you will find that the third derivative is equal to A cube, right? Is equal to A. So which means we can write f of d EAX as A naught, this one, d3 EAX, d3 can be replaced by A3. So A cube EAX plus A1 A square EAX plus A2 AEAX plus A3 EAX. Here if you notice, EAX is common again, so we can take it out. So AO A3 plus A1 A square A2 plus A2A plus A3 times EAX. Now here if you notice, this part can be written as f of A. So which means our equation becomes f of DEAX is equal to f of A EAX, which is what we had to prove. Okay. Similarly, there is another result. F of D EAX times V is equal to EAX f of D plus A V. Now here V is a function of X. Now let's again see how it can be proved. F of D EAX times V is equal to, now this can be written as A naught D3. Again we are going up to the third successive differentiation. D3 plus A1 D2 plus A2 D plus A3. And what we are left with here is EAX times V. Now let's distribute EAX times V. We get D3 EAX V plus A1 D2 EAX V plus A2 EAX V plus A3 EAX V. Now again we have to take care of this. So let's differentiate D3 EAX V. Now remember here it is a combination of two functions of X. So let's apply the Leibniz theorem for successive differentiation. So what do we get? We get A3, because 3 times if we differentiate e to the power of AX, we get A cube EAX V. V remains as it is. Now remember the coefficient is 1, and just remember the Pascal's triangle 1 3 3 1 because it is cube. Okay, so 3, this becomes a square EAX, and this becomes dV, first derivative, plus 3A EAX, and this becomes the second derivative of V, and this becomes EAX, the third derivative of V with respect to X. So now here EAX is common. Similarly V common. So let's take it out. So EAX, we get A cube plus 3A square D plus 3AD square plus D cube, and V is common. Now EAX, now this whole thing can be written as D plus A cube. Yes, algebra, high school algebra. X plus Y cube is equal to 1 cube, X cube plus 3 X square Y plus 3 XY square plus Y cube times V. Similarly, this one would be second successive differentiation will lead us to EAX D plus A square V, and first derivative would be EAX D plus AV. Now we had reached up to f of d of EAX times V is equal to A naught D cube EAX V plus A1 D square EAX V plus A2 D EAX V plus A3 EAX V. So now we can do some substitutions. So A naught, now this is going to be this. So EAX A naught D plus A cube V plus A1 EAX D plus A square plus A2 EAX D plus A plus A3 EAX. Okay, so that's where it's, and V. Okay, now here this is common. V, here I missed a V and here I missed a V, so this is common. So let's take it out. EAX V A naught D plus A cube plus A1 D plus A square plus A2 D plus A plus A3. Now this part can be written as f of D plus A. Remember, this is f of D EAX V, and this is what we set out to. Okay, there is one more result that's very useful, and that is, till now we have looked at f of D. Now we are looking at f of D square cos AX is equal to, remember when I said D square, here we are talking of second derivative, is equal to f of minus A cos AX. Okay, let f of d square be equal to a naught d4 plus a1 d square plus a2. Had it been f of d, we would have taken a naught d square plus a1 d plus, so this is of degree 2n, where n is equal to 2. Okay, now let's take it forward. F of d square cos ax is equal to a naught d4 plus a1 d square plus a2 times cos ax. Now we can write this as d square plus a1 d square plus a2 cos ax. Now we know d square is equal to a square, which implies that minus d square is going to be minus a square. Why we are getting into this is because we want minus a, right? So since this is the case, then times minus a square plus a1 minus a square plus a2 cos ax, and this is nothing but f of minus a square cos ax, which is what we set out to prove. Now similarly, we can show that f of d square sin ax is equal to f of minus a square sin ax. Okay, I think that's enough for today. Bye for now.